These giant transformers don't power homes directly. Instead, they make long-distance electricity transmission possible. It all starts with precision-cut electrical steel laminations. Every power transformer has two main components: the magnetic core and the windings. The magnetic core is assembled first by stacking thousands of insulated electrical steel laminations. Using thin laminations instead of solid steel dramatically reduces eddy current losses. The magnetic core itself consists of three main limbs, one for each phase. The large steel frames at both ends are structural supports that clamp the assembly together, keeping it rigid during transportation and under the enormous electromagnetic forces produced during operation. The three limbs are connected by upper and lower yokes, forming a closed magnetic circuit with a very low reluctance. Each limb is then covered with layers of cellulose insulation. Besides electrically isolating the windings from the core, these insulation barriers establish the required dielectric clearances and create oil ducts that carry heat away during operation. Before the transformer windings are assembled, the insulation system must first be built. Rings, cylinders, spacers, and support blocks are precisely machined from high-density cellulose pressboard. Together, these components position each winding with millimeter accuracy, creating controlled oil channels for cooling while maintaining the electrical clearances required to withstand hundreds of thousands of volts. The winding assembly can only begin once this insulation structure is complete. With the insulation framework complete, the transformer windings begin to take shape. Each winding is built from insulated copper conductors, carefully arranged into multiple discs and layers rather than a single continuous coil. Between these sections, cellulose spacers maintain precise distances and form a network of cooling ducts that allow transformer oil to circulate throughout the winding. This construction removes heat generated by electrical losses while keeping the temperature evenly distributed. The layered structure also controls the electric field inside the winding and provides the mechanical strength required to withstand the enormous electromagnetic forces produced during short-circuit conditions. Each phase of this generator step-up transformer contains two separate windings. The inner low-voltage winding is connected directly to the generator, receiving electricity at generator voltage. Surrounding it is the high-voltage winding, which contains many more turns and raises the voltage to transmission levels before the electricity enters the power grid. Although completely insulated from one another, the two windings are magnetically coupled through the transformer core, allowing electrical energy to be transferred efficiently without any direct electrical connection. Once the windings are complete, they are dried in a large industrial oven to remove moisture from the paper insulation. Only then are they ready to be assembled onto the transformer core. The next step is to combine the transformer's core and windings into a single active assembly. The upper yoke laminations are temporarily removed, allowing each winding to be positioned over its corresponding core limb. After all three windings are precisely aligned, the upper yoke is reassembled, restoring the closed magnetic circuit. From this point on, the core and windings form the transformer's active part, the heart of the entire machine. Because the transmission grid does not always operate at exactly the same voltage, the transformer's output voltage must be continuously regulated. To achieve this, an on-load tap changer is connected to the high-voltage winding, where multiple tapping points are brought out along the winding. By selecting different tapping points, the transformer changes the effective number of turns on the high-voltage winding, adjusting the turns ratio and therefore the output voltage. During each tap change, the diverter switch transfers the current through a controlled transition path, allowing the winding connection to change without interrupting the flow of electrical power. Elsewhere in the factory, the transformer tank is fabricated from heavy steel plates. Later, the lower tank and removable cover will be sealed together, enclosing the entire active part in insulating oil for both electrical insulation and cooling. With the active part sealed inside the tank, the transformer enters its final assembly stage. The high voltage and low voltage bushings are installed, providing the insulated electrical connections between the internal windings and the external power system. Additional components, including the cooling system and monitoring devices, are also fitted, completing the transformer. Before leaving the factory, every unit undergoes a comprehensive series of electrical and mechanical tests to verify its insulation, performance, and reliability. Once testing is complete, many external components, including the bushings, are carefully removed to reduce transport size and protect them from damage. At the installation site, these components are reassembled. The transformer is vacuum processed and filled with insulating oil, and after final commissioning tests, it is ready to energize the transmission grid. These giant transformers are just one part of a much larger power system. After leaving the generator, electricity is stepped up to hundreds of thousands of volts before entering the transmission grid. At these extremely high voltages, the same amount of power can be transmitted with much lower current, dramatically reducing losses over long distances. As electricity approaches cities, factories, and residential areas, it passes through another series of transformers that gradually reduce the voltage to practical distribution levels. From there, smaller distribution transformers provide the final voltage reduction before electricity reaches the homes and businesses that use it every day. The manufacturing process of a distribution transformer follows many of the same principles as its high-voltage counterpart, but on a much smaller scale. It still uses a 3-limb magnetic core and insulated copper windings. However, because the active part is significantly lighter, it does not require the large side support frames used in heavy power transformers to withstand transportation and mechanical forces. After the windings are assembled onto the core, the active part is thoroughly dried to remove moisture from the cellulose insulation. The winding leads are then carefully routed and connected to the bushings and tap changer, completing the main electrical connections before the active part is installed inside the transformer tank. Unlike massive power transformers, these smaller distribution units can be fully assembled, oil-filled, and tested before leaving the factory. Once the active part is sealed inside the tank, a vacuum process removes trapped air and residual moisture from the insulation system. Insulating oil is then introduced, filling the internal spaces and impregnating the cellulose insulation. The oil provides both electrical insulation and an efficient path for carrying heat away from the windings and core. Finally, each transformer undergoes a series of electrical tests to verify its voltage ratio, insulation integrity, losses, and overall performance. Once these tests are passed, the transformer is ready for delivery and installation on the distribution network.